You have set your delta T minimum, you have identified your pinch point, and you have started matching streams. But suddenly, the math breaks. You have a temperature violation you cannot fix, or your utility targets are way off. The problem? You are not dealing with a single pinch problem, you are trapped in a multi pinch network. In today's lecture, we are not just clicking buttons in Aspen and Excel. Today, I am going to show you how to identify and design multi pinch heat exchanger networks using Aspen Energy Analyzer and verifying the calculations using Excel step by step. If you want to stop guessing and start designing, let's dive in. Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, our topic is the design of heat exchanger network, and for this we will be taking the multi-pinch problem. By the end of this lecture, you will be able to number 1, understand what a multi-pinch problem actually is. Number 2, identify intermediate pinch violations. Number 3, apply pinch rules correctly in multiple zones. Number 4, design a feasible heat exchanger network using Aspen Energy Analyzer. And obviously, we will be using Excel for the calculations. Now, these are the three main regions. Once we talk about the multi-pinch system, that there are two pinch system. In the previous systems, obviously, one was the above pinch and the other one was the below pinch. That was for single pinch. However, once we talk about the multi-pinch system, there are three zones. Above the highest pinch, below the lowest pinch, which we call as below cold pinch, above the highest pinch, we call it as above hot pinch, while this region 2 is the intermediate region, and this is the critical region. And this is the point where most of the students or engineers make the mistake. If we look at one by one, above hot pinch, we obviously require the hot utility. The heat source is hot utility. The heat sink is cold process streams. We have already studied that number of hot streams and the Cp of hot stream should be less than equal to Cp of cold stream. If we go down to below cold pinch or below pinch system, that only cold utility is required, heat source is hot process streams, and here we have studied that the number of hot streams should be greater than equal to number of cold streams, or it could be equal to, and similarly the Cp of hot stream should be greater than or equal to Cp of cold stream. The heat sink is cold utility. Now once we come to the intermediate pinch, it is bound by two pinch points. Obviously, this is first pinch point and this is the second pinch point, and between these is we call as intermediate pinch region. It acts as independent pinch. There is no utility required. Process streams exchange heat between themselves and everything is sorted out, but it could be tricky at times once there are temperature violations. Similarly, there is another example, or there is another representation of upper pinch, that no heat transfer across the pinch, no external cooling, only hot utility required. For below pinch, cold utility is required. And for intermediate zone, the process to process heat recovery is required to achieve the objective. So for today's system, we have been given the streams data, and the value for delta T minimum for today's lecture is 20 degrees centigrade. We have two hot streams and two cold streams. So the first hot stream is from 150 to 50 degrees centigrade with the Cp of 0.2 megawatt per degree centigrade, and the total heat load is 20 megawatt. For second hot stream 170 to 40 degrees centigrade, the total load is 13 megawatt. For third stream, which is the cold stream, 50 to 120 degrees centigrade, total heat load of 21 megawatt. For fourth stream from 80 to 110, which is cold stream obviously, the total heat load is 15 megawatt. Now we will use this information, but before going to that, we have been also given the utility data that the cooling water is from 20 to 30 degrees centigrade. The MP steam temperature is from 180 to 179 degrees centigrade. Previously, we had taken the utility data by default from Aspen Energy Analyzer, but today we will put our own values over there. So using this information, we will now move to Aspen Energy Analyzer. We will add the process streams, we will add the utility streams, and obviously we will design our heat exchanger network for this multi-pinch problem. So coming to Aspen Energy Analyzer, we will first create our case, and we will first add H1, H2, C1, C2. These are our 4 process streams. We have data in Excel, so I will simply copy paste the data of T in and T out, which is the inlet temperature and outlet temperature. For Q, 20 megawatt, 13 megawatt. So 20 megawatt, 13 megawatt for hot streams, while for cold streams, 21 megawatt and 15 megawatt is the information given to us. If we go to the energy targets, we will first select delta T minimum as 20. So heating load required is 10,000 kilowatt, while the cooling load required is 7,000 kilowatt. But the most important thing is this one, that the pinch temperatures, there are 2 pinch points. So first one is hot pinch is 100 degrees centigrade, cold pinch is 80 degrees centigrade. The second system, or the second pinch, is that 70 degrees centigrade is hot pinch temperature, while 50 degrees centigrade is cold pinch temperature. So it will be really interesting how we can solve it. But obviously, first we need to add the utility data. So we will come to the utility streams. We will add the MP stream, but we will specify our temperatures 180 to 179 degrees centigrade. And in cooling water, we have been given 20 to 30 degrees centigrade. So now all the values are now available. Total minimum is 5, minimum for MER is 8. So we have to at least specify or design 8 heat exchangers in our network. So now we will come here and we will first click on this to show height pinch lines. And now you can see there are 3 zones in the system: above pinch, intermediate region, and below pinch. Now, if you look at the above pinch system, there are 2 hot streams and 2 cold streams. So the rule is specified that of number of streams. If you look at the below pinch, there is no cold stream. So obviously these 2 hot streams will exchange heat with this cooling water. While in the intermediate region, where there is no rule regarding the number or CP, these streams can exchange heat with each other. So there is no utility required over here. Now I will take you to the Excel sheet now, and we will first build the heat exchanger calculations for above pinch system. And we have been given the hot pinch temperature is 100 degrees centigrade, cold pinch temperature is 100 degrees centigrade. So the outlet temperature of hot stream will be changed. Similarly, we have been given the cold pinch inlet temperature is 80 degrees centigrade, while this stream is by default at 80 degrees centigrade. And if I take you back, this stream C2 is already above pinch. There is no portion of it left below pinch or in intermediate region. Now, if you see, Cp of hot should be less than equal to Cp of cold, and it complements or it does not violate in any case that if we connect this with this or H1 with C2, rule does not break. Similarly, H2 with C1 or H2 with C2, rule does not break. But similarly, we can see that the total load here is 17,000, while here it is 27,000. What we need to do, we will first connect this stream, which is our H1, with this stream, which is C1. So we will connect H1 with C1 over here, and 150 to 100 degrees centigrade, 82, obviously it goes to 113.3. Connect H2 with C2, 170, 100, 82, 94. Now for remaining load, it will exchange it with MP stream. So this is connected with this one, tying it, connected, and similarly for this one, it will be tied, and again, you can see this stream is now fully specified and eliminated from the system. So this is how we have solved above pinch system. Now we will go to the intermediate system, and again I will take the data from here and It is 100. It is 100 because 150 to 100 is utilized here. Now it will start from 100 and it will end at 70 degrees centigrade because the above pitch temperature is 70 degree centigrade. The stream is already eliminated, while it will start from 50 because the cold pitch temperature is 50 degrees centigrade. This temperature will be 80 degrees centigrade. So I will specify what I have changed because it is from 80 to 120. So from 50 to 80, it will be coming here. Its load is, the heat load is for hot stream is 9,000 kilowatt, while that of the cold stream is also 9,000 kilowatt. So it is very simple case. We have to connect properly. So we will first connect like H2 with C1, and similarly from 100 to 70 degrees centigrade, and this is from 50 and it has gone to 60 degrees centigrade. And similarly for this one, for H1 with C1, 100 to 70 degrees centigrade and 60 to 80 degrees centigrade, 20, 10, and here it is 20, 40. Now for this system, there is no cold stream here. So obviously these two hot streams will exchange heat with the cooling water. Very simple case, just connect it. There is no need to go back to Excel. And you can see this has been done. And similarly, this has been done by tying, and you can see our complete network has been solved over here. And you can see that we have successfully solved our multi-pinch system, or we have designed multi-pinch system using Aspen Energy Analyzer. If you look at the units, there were 5. The load is the same, like we'll see. It is 7,000 and it is 10,000 kilowatt. If you look at here, that number of units are same as were defined in the target zone. Here is something most lectures won't tell you. Multi-pinch problem often require stream splitting, intermediate utilities, iterative redesign. We have just solved a very basic example. In the upcoming lectures, we will consider these points. And this is why real industrial heat exchange network design is not straightforward. If you found this lecture useful, make sure to like the video, share with your classmates, and subscribe for more advanced process design concepts. Next lecture will cover on how to handle utility optimization in multi-pinch systems. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.